So last time we were looking at sound and resonance, and I sort of have like a little blurb here from our last video about using resonance, and it was all about creating the standing waves and structures and getting the structures to actually vibrate naturally when the waves fit nicely, which amplifies the sound. I showed you a few things about resonance last time. So we're going to look at a few different ways this is actually done with different structures, especially for like musical instruments and stuff like that. And one of the more common things that is used to create sound is strings, like in guitars, pianos, and that type of stuff. And typically for most of these types of structures, usually the string is tied between two posts, or whatever you want to call them, and it will then bob back and forth and make a standing wave. So let me just show you something really quick on what this actually looks like. Oh, that's it right there. Okay, so this is like a little video from YouTube that shows it really nicely. So you got a string here, it's hooked up to a really fast vibration type thing, but it shows it really nicely sort of how this works. So there's the string vibrating back and forth, and that is literally what a guitar string or piano string or a violin string or any stringed instrument actually looks like. And if we actually look, this is sort of like a trough right here. I don't know if I can pause it. Let's see, there's a nice trough right there, but that's just a trough. And then when it bobs up, it's a crest. It sort of bobs back and forth. So since you only have either a trough or a crest at any given time, you never actually have the entire wave, okay? And if we keep on going, they increase the frequency, and as they increase the frequency, they change the wavelength. So now you have a trough and a crest. This is one full wave, and this is a higher frequency. So before we just had a trough or crest, now we have the entire thing, okay? And if we go even faster, instead of having 2 bumps, if they go even faster, now you can actually get 3 bumps involved. So again, this is a higher frequency, lower wavelength, and with guitars and different musical instruments, instead of causing the string to vibrate faster or slower, you just push down with your finger or whatever mechanism is being used in order to make the actual functional vibration longer or shorter. And that's basically how it works. Okay, so for example, the first one here, when it was vibrating here, we have the length of the string. I'm going to call that L. L will be the length of the actual string here. And here, the length of the string is just half of a wavelength. It's either a crest or a trough. That's all it fits on the string. And that was the first one that I showed you. And this would be the first frequency that is possible. Then what they did is they actually vibrated it quicker. It was the same length, but now you had something that looks like this bobbing back and forth, and now the length is equal to the wavelength, and this would be the second frequency that's possible. Then they went even more. Okay, they had it vibrating even faster, and it looked something like this, and now the length is actually 1.5 waves, and this would be the third frequency possible. And if we label different parts to it, there's like the nodes and the antinodes. The nodes, of course, is where the standing wave doesn't move. So there's a node, there's a node. We always have nodes at the end because that's where it's tied, but now we also have nodes here and there, and here where it's not moving. And if you also remember, there's also antinodes where it moves the most. So there's an antinode, there's an antinode. These are all antinodes where you have your maximum amplitude. So you have nodes and antinodes created within the string in order for it to work. And you have your first frequency, your second frequency. In fact, your second frequency here, this would be exactly 1 octave higher than this one because the string has been cut in half. And every time you make the string half as big, it goes up 1 octave. This is actually first really analyzed by Pythagoras, believe it or not, way back when. That's one of the reasons the musical scale is unbelievably mathematical. Okay, now you don't always have to use stringed instruments. We often use tube instruments, use tubes of air. So aside from strings, we also use tubes of air in order to make this work. And again, it's all about having the vibration and making things fit. So let's actually start by here. I'm going to draw a tube like this. Except what I'm going to do is I'm going to get rid of the ends. something like this. And we'll do a couple. So I'm going to make a couple here actually. So copy paste it, and we'll do another one. There we go, something like this. Okay. So this would be like a trumpet or a trombone, something where the, both ends are actually open. So tubes of air are often used as well. Now, if we can start like the biggest wave you possibly can fit in one of these things, well, this end over here, that has to be an antinode because it's wide open and can move. Same thing here. They'll always have antinodes at the ends. And then when you put the waves in, the biggest wave I can put into this tube would look something like this. And then it would sort of flip-flop back and forth. So I end up actually having a node in the middle. And this would be like a trumpet, trombone, any kind of wind instrument like that where you're vibrating your lips at one end, sound comes out the other end. And if you look at how much of a wavelength this is, it's starting at the top at the crest and goes to the bottom of the trough. The length of this tube is half of a wave. Now if I go to the next one, if I increase the frequency of the vibration, the next biggest wave I could fit in here would look something like this. And this would bob back and forth. And now we have a couple nodes in here. There's a node there, there's a node there. And now we have one wave fitting here. So the length is actually an entire wavelength. And again, this will change the tone. So sometimes wind instruments will change the tone by adjusting the frequency of the vibration of the lips, or you push the valves or move a slider or something like that to change the actual functional length of the tube, which then changes the wave that will fit, which then changes the frequency. If we go to the next one that would actually fit would look something like this. And that would bob back and forth. And you can see we've got a few nodes in there and stuff like that. And now I've got, well, there's a whole bunch of waves in here, but if you go down here, that's one wave plus half a wave. So now the length of the tube is 1.5 wavelengths. Okay, so very similar to the string type idea. Now, not all tubes of air are actually sealed. Sometimes tubes are open. So we go back to the same type of tube, like this, except what we can do is we can also seal off the end again, something like that. So not all wind instruments are sealed or open at both ends. And we will, let's copy that and paste that. Okay, something like this, do a couple of these guys. Some instruments are sealed at one end, so like a flute idea or something like that. And if we look at these guys as well, we can do the same type of analysis. So biggest difference here is this end is open. So once again, we'll have an antinode here. These will all be antinodes. But this end is now sealed. So since that end is sealed, we want a perfect reflection and have it create a node. So the wave actually is put in here. It looks a little differently. So we've got antinode there. It's going to come together. And then there's the reflected part right there. And that bobs back and forth. And it looks something like this. And so this is a little bit different. So now if we look, that's the top of the crest. And that's the rest position. The length of the tube is actually just 1/4 of a wavelength. And if we go to the next one that sort of fits would look something like this. Something like that, and that's going to bob. Now we've got a little node in there, but it's going to bob back and forth. And now we have 3/4 of a wave actually fit inside. And if we do the next one, it's going to be kind of tricky to draw. We'll do our best here. I know I have to have a node over here, but it would look something like that. A little rough, but that's okay. And now if we look at how much a wave here, let's see, that would be one complete cycle. That's one wave and 1/4 wave. So this is actually 1 1/4 waves fitting inside. So it actually goes up by half a wavelength each time, just like the other ones, except it starts at 1/4 wave instead of a half wave. Okay, so these are all the different basic ways that music is produced in pretty much every single instrument on the planet. And these are the properties are used as well in different structures to resonate sound and that type of stuff. Okay, so it's kind of interesting how this type of stuff works. But musicians know an incredible amount about resonance and the way the instruments are designed, the bodies of the guitar, especially grand pianos and all that kind of stuff. huge applications of resonance and making sure all this stuff works fine. And when they tune things like guitars and that type of stuff, what they're often doing is they're changing the tension, which changes the speed of the wave, which then in turn it changes the wavelengths that'll fit nicely within it, so you get the right frequencies. Okay, so let's show you something else that's also involved with this type of stuff. Okay, so let's use this. Suppose we have two wave sources. We've got a white wave source and a green wave source, and they are perfectly synchronized with each other. You would hear this yellow one. They're going to have constructive interference, and everything's synchronized. You are going to get a really good wave. This is going to give you really good resonance, causing one thing to cause vibrations in the other, perfectly synchronized. Okay, now we can actually adjust this a little bit. If we actually change the situation a little bit, something like this, where we've actually taken one of the waves and we've shifted off by half a wavelength. Instead of crest on crest, now we have crest on trough. They will actually cancel out and you'll actually get no sound. This is how noise canceling headphones and noise canceling technology works, is what a little receiver does in the headphones is it actually picks up the sound waves from outside the headphones and then produces a secondary wave to actually cancel out the initial wave. And that's how noise canceling headphones work. Not noise isolating, that just muffles stuff, but noise canceling actually analyzes sound waves and then produces opposite ones. That's why noise canceling doesn't work for quick, sharp sounds, because it doesn't have time to analyze it and figure out how to cancel it. It's for like the general background noise that's kind of consistent. That's the type of thing that actually does. Okay, but let's go back to this. Now, what happens if the two waves aren't perfect? What if I change the green wave just a little bit? Well, if I change the green wave a little bit, they're no longer perfectly synchronized. This isn't going to give good resonance. It's not going to work very well. And you can see it pulses in and out. And this is something that's called beats. And this happens quite a bit, especially with music tuning and music classes and stuff and bands. You get something called beats. And the further apart the frequencies, the more rapid the beats become. Okay, so we're going to look at this for just a little tiny second. So if you have two very close frequencies, you are going to have not perfect resonance is going to occur. So it's not going to work very well. Okay, what you end up getting is you actually hear a pulsating tone. For example, let's say you have two tones are really close. Suppose you got like 500 hertz and you have 510 hertz. Well, the frequency you'll actually hear, you won't actually hear either of these, you actually will hear 505 hertz. You'll actually hear the average, except this will actually pulsate in volume. And this is what you call beats. Okay, so this is what's called beats. You'll actually hear the average frequency. This is the average frequency between the two. So you actually hear the average frequency of the two sources, but it'll pulsate in volume. Okay, so let me see if I can show you something with that. Okay, so let's see if I can actually show this to you. Let's see if this will actually work or not. It's a lot harder not doing it in the lab, but we'll try this. So suppose I got two sources, both 200 hertz, and then we'll get them going here, and hopefully using the little laptop thing here, recording is going to work. But this tone is two sources at 200 hertz. So I know it might be annoying, but so they perfectly match, which work really well. So what if I change one of them to 201? Now they aren't perfectly matching. They're not going to resonate as well. So now you won't hear 200, you won't hear 201, you'll actually hear 200.5 hertz, and it sounds like this. And that's the beats. So it's 200.5 hertz but pulsating. And if I make it go even higher at 202, now you'll hear 201 hertz, it's the average of the two, and it'll pulsate quicker. Okay, so that's how beats works, and hopefully you're able to hear that okay through the video. And this is how professional musicians and conductors will often tune instruments in bands and that type of stuff, is they'll tune them to each other, and they're listening for that pulsating beats tone type thing to figure out how closely tuned the two instruments are.